x is equal to 1 over a root of p of x. So there you go. That's point number one. Very interesting. Hello everyone, this is allLogarithmsWereCreatedEqual with a third installment in Polynomials' Greatest Hits. Now what I need to explain first is something called Polynomial Reversal. And this is a process where we basically reverse the order of the coefficients in a given polynomial. So with our typical general definition of a polynomial, we basically have p of x as it's defined right here. We can take the reversal of this polynomial, and formally defined, what this equals is x to the n times p of 1 over x, where n, of course, is the same integral degree number as the original polynomial, p of x. So, for example, if we just make up an example, like I have right here, g of x, then there are a couple of ways of logically deducing the reversal of g of x. So, perhaps the most direct way, perhaps, would be just to use this definition here, and substitute 1 over x for x in this original polynomial, and then multiply by x to the sixth, since this is a sixth degree polynomial. So, in that case, the reversal of g of x equals, this is after substituting 1 over x in the original polynomial g of x, so you can clearly see what that equals. It's, wherever we had an x in the original equation, we just substitute 1 over x. And now, after that, we can distribute x to the sixth to each term, getting this result right here. And we can rewrite them in order of decreasing degree. We could also rewrite this as this result right here. And what you'll notice about it is that basically all we really did was reverse the order of the coefficients of g of x. So, negative 7x to the sixth comes from this constant, negative 7, in the original polynomial. And, we have a plus 5 for x to the first. Well, the plus 5 is applied to x to the fifth in this case. Notice, of course, how the coefficient of x to the fifth in the original polynomial was 0. We really had no x to the fifth term in the original one. And similarly, we have no x term, x to the first, in the reversal. And that's the reason why. The reason is because the coefficient of x to the fifth in the original polynomial was 0. And in my opinion, something that also helps demonstrate or even determine what a polynomial's reversal is kind of just a method where we basically list all of the coefficients of the original polynomial and then reverse them, because that's basically all we're doing. And, we can make that clear if we simply, with this example, for instance. So for g of x, what you'll notice is that the coefficients going in decreasing degree, starting with 6, which is equal to n, n equals 6 in this case, so we can start with the coefficient 1, because it's 1 times x to the sixth. The next one we should list is 0, actually, because there's a 0 times x to the fifth kind of hidden there. We don't see it when we write it out explicitly, but, we need to make sure that we keep track of it, because that'll be important later on. For the x to the fourth term, the original coefficient is 3, and for the next one's going to be the coefficient of x cubed, so it's negative 1, and after that we get 3 more coefficients, and they're in order, just reading them straight from this original polynomial, we get 4, 5, and negative 7. Now what we can do from here is simply read off each of these coefficients in backwards order, and those are the coefficients of the reversal of g of x. And also I'd like to point out that the degree of a reversal of a polynomial is equal to that same number, that is the degree of the original polynomial. So they share the same degree, by definition. And so as you can see, hopefully it's made clear in this format, or in this, listing, that basically we're just kind of reflecting the coefficients. And, in this particular case, since the degree is even, one of the coefficients applies to the same degree polynomial, and that is the negative x cubed. Now, on to the fun part, the interesting part. I actually have a few related facts about this simple process, or seemingly simple process, that I'd like to prove for you. Number one, the roots of a reverse polynomial are always the reciprocal of the original roots. And so I can prove this for you. This is one of the things that I proved as part of a mini-course. We know by the fundamental theorem of algebra that it is expressible as the product of all these binomials, x minus r sub I, representing each of the n roots to this polynomial of degree n. And this is, of course, taking account for complex roots and, multiplicity, things like that. That's just the fundamental theorem of algebra, though. So, I'm going to define capital R of x as the reversal of p of x. So, by definition, R of x equals x to the n times p of 1 over x. And so, by substitution, we can actually consider what this product actually is, especially using the second line right here, involving p of x and each of the n complex roots. So, what this is, by substitution, is this result right here. And we can get this from line 2, just substituting, this is times p of 1 over x. So, in this line, whenever we see an x, we can substitute 1 over x, and that is a component of the definition of R of x. So, by definition, we know R of x equals x to the n times, 1 over x minus r sub 1 times 1 over x minus r sub 2 quantity times 1 over x minus r sub 3, that quantity, times all the way until we get to the quantity 1 over x minus r sub n. So, it's the product of all of these binomials. What's interesting, however, is that we have exactly, by the fundamental theorem of algebra, we know we have exactly n complex roots. So there are n r sub n's, or r sub i's, I should say. So n of these binomials that are part of this product. And since we also have an x to the n as a coefficient in front, so to speak, that's another part of the product, we know then that there is a one-to-one correspondence. There's exactly one x being multiplied in this entire product for every root that exists. So for each of the n roots, there's exactly one power of x, so to speak. So as a result, you can probably see where this is going, we can take each of those x's and distribute it to each of these binomials. So, in other words, we can have one x that is distributed into this binomial, another x that is distributed into this binomial, and keep doing that for each of those component factors, those binomial factors. And we actually get something very interesting, as you would imagine, since we're doing this for every single root, so it's a very consistent kind of thing. So what we get as a result is, now we have a nice representation, or rather fascinating formula for what R of x really is, in terms of its, in terms of actually the roots, r sub 1, r sub 2, r sub 3, which, by the way, are the roots of the original p of x. So, what can we do from here? Well, we can determine, in the general case, what the roots of R of x are. just based on this representation. Basically, the reasoning for that is that it's simply of a form very similar to line 2 right here. So through the substitution, we get a very similar structure. That is, a product of several binomial factors. So, a natural question to ask is, when does capital R of x equal 0? Well, it equals 0 whenever one of these binomial factors equals 0. So, r sub x equals 0, in other words, we're finding the actual roots, the values of x, that make r of x 0. So, and this is an important result, if r sub x equals 0, excuse me, damn it, I did it again. If capital R of x equals 0, then we know one of these binomial factors must equal 0. And what we've shown in this way is that in order for one of them to equal 0, x must be representable as the reciprocal, or the multiplicative inverse, of r sub I, where r sub I must be a root of the original p of x. So, that's pretty cool, isn't it? Right? So we can logically prove that. Now, as you can see, hopefully this makes sense. If one of these binomials equals 0, then 1 must be equal to x over r sub I. And thus, r sub I must be equal to 1 over r sub I, for whichever root that is. We're just saying there are n roots, and, n binomial factors, so one of those, at least one of those binomial factors must be equal to 0, so, for whichever one that is, x is equal to 1 over a root of p of x. So, there you go. That's point number 1. Very interesting. Now, we can combine this fact as well with our shorthand sum of roots formula, which you can see in a previous episode, actually, of Polynomials Greatest Hits. But the long story short is that we know that the sum of all complex roots, r sub I, equals negative a sub n minus 1 over a sub n, for any general polynomial. And we've proven this before, actually, in a previous episode. But that's a very interesting formula. I hope you've watched that episode, for that matter. Hopefully I'll leave a link or something. But the point is, we can use the sum of the roots formula for what we can do is applying that formula for the sum of all the roots with regard to capital R of x. What we know is, so we know that the sum of the roots for capital R of x must equal negative b sub n minus 1 over b sub n, where I'm referring to b sub n as being, or b sub k in general, for being the kth coefficient in the polynomial expansion for R of x. So, and another thing we just learned is that the roots of r sub x are each expressible as, the reciprocal of the roots for p of x, so we can rewrite this as the sigma, the sum from I equals 1 to n of 1 over r sub I, where again r sub I refers to a root of p of x. And another change we can make, well, actually, let me just write that. So we know that that equals negative b sub n minus 1 over b sub n. But we also know, bear in mind, that the coefficients for capital R sub x are, by definition, the reversal of the coefficients for p of x. So, as a result, where we now have negative b sub n minus 1 over b sub n, we can also replace that side of the equation with the corresponding coefficients of p of x. So, when we think about it, we know that the first coefficient of r of x, b sub n, must be equal to the last coefficient of our original polynomial, p of x. So, b sub n must be equal to a sub 0. And additionally, we know that the second, and I'm saying second, coefficient, what I really mean is the coefficient of x to the n minus 1, in R sub x must equal the second to last coefficient in P sub x, which in this case must be a sub 1. Because there is such a correspondence between the coefficients of R of x and P of x, we can rewrite this formula in a very interesting way. So finally, our final fact in this track, we know that the sum of the reciprocals of each of the roots of P of x must be equal to negative a sub 1 over a sub 0. So that's, again, a very general, elegant kind of answer or solution that gives us a new understanding about any general polynomial. Because again, this works for any general polynomial. This formula is very general. We didn't make many assumptions at all about P of x. We just said it is some general polynomial with complex coefficients, and went from there using, fundamental theorem of algebra and everything else. But it's very interesting, is what I'm telling you. I can tell you what the sum of the reciprocals of the roots are just by looking at the ordinary polynomial expansion of any polynomial you can possibly think of. So, thank you very much for watching. I hope you enjoyed that. Yeah, I hope you enjoyed learning this. Let me know if you have any questions or additional exercises or thoughts or anything. But yeah, I think that's enough for this episode.